star the magnetar evolved from had the mass 30 to 40 times that of our Sun. The matter in these stars is dense to such a point that a fountain pen cap would weigh billions of tons, and a human would be torn to bits within a matter of seconds after landing on the star's surface. Several years ago, astronomers from NASA managed to register a phenomenon which came to be known as a starquake. Thanks to the Fermi Gamma Ray Space Telescope, scientists received data about intense X-ray bursts. Their source was magnetar SGR J1550-5418. The magnetic field of this star is so powerful that from time to time its crust bursts with vast amounts of energy released through the crack. Such starquakes are the source of pulsed electric current. In theory, if a magnetar of this kind at its most active were to find itself within the boundaries of the solar system, we wouldn't as much as notice the threat, as the ozone layer of the Earth, together with all organic life forms, would be wiped off within a matter of a few hundredths of a second. Fortunately, however, the magnetar closest to us is a safe enough distance away. A magnetar is hard to approach not only due to the gravitational properties of its core and energy flares at the time of a starquake. When a magnetar is in its stable condition, its magnetic field is able to mess with electric devices hundreds of thousands of kilometers away, and within the radius of 1,000 kilometers, any object would be reduced to atoms. In order to systematize the difference in their radiation, scientists decided to divide magnetars into two varieties by using abbreviations. Rather than the full names, you will see these in any astronomical catalog. SGR, soft gamma repeater, and DXP, anomalous X-ray pulsar. In essence, SGR and DXP are different phases in the life of one and the same object. According to scientists, a magnetar exists as an SGR pulsar for the first 10,000 years. That is, it's a pulsar visible in regular light and repeatedly emitting bursts of soft gamma rays. As time goes by, it exhausts its properties and recedes into the invisible spectrum, when it can be seen to us only in the X-ray range, as an AXP. According to different sources, today among billions of neutron stars, the number of known potential magnetars ranges from 30 to 150. There are about 12 of them in the Milky Way. The magnetar is a soft gamma repeater, and if a starquake were to take place on its surface, it would affect us only by some slight changes in the top layers of the ionosphere. Due to their small dimensions and remoteness relative to the Earth, magnetars cannot be observed through regular amateur telescopes. The method of infrared or X-ray scanning of the sky is usually employed to observe them. Nevertheless, thanks to their active magnetic field emission and radiation, these stars are much easier to detect with the use of various instruments. This is exactly what took place several years ago, in 2013. Astronomers claimed to have discovered a magnetar in close proximity to a supermassive black hole right in the middle of the Milky Way. The star was detected thanks to several orbital telescopes, including the Chandra X-ray Space Observatory. SGR 1745-2900 is only 0.3 light-years away from the edge of the black hole, and to date it remains the only neutron star to have been discovered in close proximity to an object of this scale. SGR 1745-2900 has been observed by scientists ever since its discovery. Several years ago, the level of its X-ray radiation was proclaimed to be significantly lower than that of the stars of this category. The news prompted numerous debates. Can these changes have been caused by the black hole in the star's environs? After 2 years of observing SGR 1745-2900, astrophysicists came to the conclusion that, all things considered, the distance of 0.3 light-years is insufficient for any interaction in the magnetic or gravitational field to take place between the black hole and the magnetar after all. The reason is likely to lurk elsewhere. A magnetar's lifespan is quite short, just about 1 million years, and it's quite natural for its magnetic field to gradually die down throughout the star's existence. Some scientists assume that these processes may be the reason for the change of the star's status. In this case, magnetars can switch their category, flare up more frequently or less often, deplete the stock of the matter, and thus go from the category of SGR to the category of AXP. In its autumn years, a former magnetar that managed to survive the dissipation of its magnetic field may even become quite a different kind of star, namely a thermally emitting neutron star. So far, just about 7 objects of the kind are known to science. For their number, this group has been dubbed the Magnificent Seven, and each of them may once have been one of the most dangerous objects of deep space. But in order to establish that, it will take us long years, further technological advancements, and dedicated people willing to devote their lives to searching for solutions to the most dangerous and incredible mysteries of the universe. A perfect example of these eerie celestial objects are black holes. Their sheer existence was considered impossible until only recently, when on the 10th of April 2019, the National Science Foundation in the USA showed the world an image revealing a black hole in the middle of the Messier 87 galaxy. This object has a mass approximately 6.6 billion times that of the Sun, with a diameter of about 100 billion kilometers. Just to compare, the diameter of the Earth is only 12,742 kilometers. This hole falls into the category of supermassive black holes. A similar object can also be found in the center of the Milky Way. It is called Sagittarius A and boasts from 2 to 5 million times the Sun's mass, according to different estimates. The diameter of Sagittarius A is 45 astronomical units. In other words, 45 times the distance from the Earth to the Sun. But is it possible to admit of the existence of even larger black holes in space? And which of them is the largest? Let's figure it out. A black hole is a term referring to an area in space with an incredibly powerful gravitation in the center. As a rule, these objects are rather small at first and are able to expand as they actively build up their masses. Black holes are categorized according to their masses. The heavier ones are called supermassive black holes. At the moment, scientists haven't formed a unanimous opinion as to how these objects come about in space. According to the most popular theory, that of gradual expansion, when a black hole appears, it has a mass typical of a star, and later on it grows by sucking in the surrounding matter. The amount of information accumulated by science about these objects is rather scarce, but even based on the current data, a supposition can easily be made about there being at least several such holes in the center of any large galaxy. In the time the universe has existed, a few million or even billion of black holes are likely to have been formed in it by now. At least today, only a small fraction of them is known to us.